In the last class, we have discussed about dielectrics. That means polar dielectrics, non-polar dielectrics, and how dielectrics gets polarized, electrically polarized. That we have. These are all discussed in the last class, right? So now let me move on to discuss about the dielectric strength. So we all know dielectric is nothing but insulators. So then what is meant by dielectric strength? For that, let us consider a dielectric, that means an insulator. Okay. Suppose if you apply an electric field to it. So if you apply an electric field, so whether it consists of either you consider a polar dielectric or non-polar dielectric. So it gets polarized. It gets polarized. As a result, the negative and positive charges are separated like this, right? They get separated. So, if we apply an electric field, so the molecules of the dielectric gets polarized and so the induced dipole moment will be produced. So if we go on increasing the electric field, applied electric field, so the polarization, extent of polarization also goes on increases, and as a result separation between the negative and positive charge also increases, and induced electric field also gets increased. In the last class itself I have told you, so when you apply electric field, so the molecules inside the dielectric gets polarized, as a result electric field gets induced, right? So when you goes on increasing the applied electric field, the induced electric field also goes on increases because the separation between the negative and positive charge also increases. So initially it was if the distance between the negative and positive is like this, so when you go on increasing electric field, it goes on increases. And finally, for example, I will tell you, suppose if you apply an electric field of about 350 volt per meter. Okay, if you apply an electric field of about 350 volt per meter, then the separation will be like this. Suppose if you increase the applied electric field to 360 volt per meter. Okay, then again, so the distance of separation between these two charges gets increases. Suppose if you apply 361 volt per meter, if you apply 360 volt per meter, then the separation will be large. Okay, so the dielectric will be insulator itself, dielectric itself. Suppose if you increase the electric field to 361 volt per meter, then this separation breakdowns and the negative and positive charges are separated like this. The negative and positive charges are separated like this. As a result, so this dielectric can easily allow the charges to pass through them. It can easily conduct the current as well as it can easily allow the charge to pass through it. That means, see, at 360 volt per meter, the dielectric will be dielectric itself. Okay, insulator itself. But at 361 volt per meter, so when you apply the electric field, so when you increase the electric field to 361 volt, then it becomes a conductor. Okay, we call this as a dielectric breakdown. We call this as a dielectric breakdown. What is meant by dielectric breakdown? Dielectric breakdown means what? That means it is a phenomenon. It is a phenomenon of a dielectric which loses its dielectric property. It's a phenomenon in which the dielectric can loses its dielectric property, insulating property, and becomes a conductor. It can conduct the current. That is called as a dielectric breakdown. That means the phenomenon of a dielectric that loses its insulating property and becomes conductor. That means it can conduct the charge. That is called as a dielectric breakdown. Okay, here at 361 volt per meter, the dielectric breakdown will take place. That means the breakdown voltage or dielectric breakdown electric field will be 361 volt per meter. But at 360 watt per meter, it is an insulator, it behaves as an insulator itself, right? No longer it can conduct the current here at 360 watt per meter. So this dielectric will be behaving as a insulator. So this is the maximum electric field that this dielectric can withstand, above which it becomes conductor. So this maximum electric field that a dielectric can withstand the electric field and so behaves as an insulator without losing its insulating property is called as a dielectric strength. Please keep it in mind. So dielectric strength is the maximum electric field with which the dielectric can withstand without losing its insulating property. That is called as a dielectric strength, and the SI unit of this dielectric strength is volt per meter. And if you consider example, so for air, the dielectric strength will be 3 into 10 to the power of 6 volt per meter. That means air will behave as a dielectric up to 3 into 10 power 6 volt per meter only. Above this value, if this value increases, then air will becomes the conductor. Up to this value, air is an insulator. And the maximum electric field that air can withstand is 3 into 10 to the power of 6 volt per meter. Above this value, it becomes a conductor. In the same way, if we consider the paper, the dielectric strength of paper is 16 into 10 to the power of 6 volt per meter. Up to 16 into 10 power 6 volt per meter, the paper will behave as an insulator, that means a dielectric. Above this value of electric field, so the paper will become conductor, capacitor and capacitance. So for that, in order to discuss this, let us consider a conductor. So in a conductor, we all know if there is no charge, then there is no electric field. As a result, there is no electric potential also. In the case of a conductor, if there is no charge inside the conductor, then electric field is also zero, then potential is also zero. If there is some charge in a conductor, due to that electric field will be produced, due to that electric potential will be developed. Right. So if there is a charge in a conductor, then obviously there exists a potential. So then suppose if we consider a conductor, as the value of charge increases, then as a result potential also goes on increases. So if the value of charge or amount of charge so present or given to a conductor increases, so then the potential will also be increased, the potential developed will also be raised. That means we can say the potential, electric potential of a conductor is directly proportional to the amount of charge given to it. Right? Means if we go on increasing the value of charge, so then the potential also goes on increase. This we can also write as the charge increases, the potential also increases. As the potential increases, the charge present in that, so obviously the charge present in that conductor will also be moved. That means the potential is directly proportional to the charge given to it. Or so if we go on increasing the value of charge given to the conductor, then potential will be rises. Okay. Now let us remove this proportionality symbol and add a constant to it. Let us take that constant as C. So Q is equal to what? C into V. Here we call C as a capacitance. That means capacitance means the capacity to store the charges in that conductor. So we can write the capacitance of a conductor as, now take this V to here, Q by V. That means the capacitance of a conductor is defined as the ratio of amount of charge given to a conductor to the potential rise. It's the ratio of amount of charge given to a conductor to the potential rise. This is called as a capacitance of a conductor. Suppose if we consider two conductors, let us take this as one conductor, or so I will take a plates, metallic plates like this. So now let us consider two conductors. Consider this as conductor 1 and conductor 2. Okay, and if this conductor 1 is charged positively, okay, then the positive potential will be developed inside this conductor 1. Let it be V1. The potential developed in the conductor 1 is V1. And the charge given to this conductor 1 as plus Q. Okay. In the same way, let us consider the second conductor. So, if we given a negative charge to this conductor, then the charge present in this conductor 2 is minus Q. Due to this negative charge, the potential developed will be V2. Since charge is negative, potential also negative, that is minus V2. Here now I will write V2 only. While taking some simplification, I will consider negative V2. Okay. So here we have considered two conductors. So conductor 1, and that is having a charge plus Q and the potential developed is V1. And conductor 2 is having charge as minus Q, the potential developed is V2. Okay. So then let us consider the potential difference. Since these two conductors are placed with certain distance of separation between them, there exists a potential difference between these two. Let it be V, potential difference between these two conductors as V. So let us consider the potential difference V as, we can be written as V1 minus V2. Here this potential developed in the second conductor is negative because the charge is negative. Therefore we can write here as minus V2. Therefore V is equal to V1 minus into minus is plus V2. This is the potential difference between these two conductors. Okay. So if we go on increasing the number of charges given to these conductors, then potential difference between these two conductors also goes on increases. That means we can write the potential difference between the two conductors that we have considered is directly proportional to the amount of charge given to those two conductors. Okay. So, or we can also write the charge given to the conductor. If we go on adding charges to both these conductors, then potential difference between these two conductors also increases. So, we can also write Q proportional to V. Okay. Now, remove this proportionality symbol and add a constant. Let us take that constant as C. So, we can write Q is equal to CV. So, here the C is a constant called as a capacitance between these two conductors. So, we can write C as Q by V. Now, we can define capacitance as the ratio of charge to the potential difference. The ratio of charge given to these two conductors to the potential difference between these two conductors. Okay. Now, what is a capacitor? This whole arrangement is called as a capacitor. Okay. So, capacitor is a device that is used to store the charges. Right. Here we are adding the charges, right? Means we are storing the charge. So, capacitor is a device that is used to store the electrical charges or electrical energy. Or we can also call the capacitor as it is a system of two conductors. It is a system of two conductors separated by an insulator. Why we consider an insulator between these two? Suppose if these two conductors are separated by very small distance, then there exists a force of attraction between these two charges. Since these two are unlike charges, there exists a force of attraction between these two. Suppose if the distance of separation is very small. As a result, these two gets neutralized. Right. So in order to avoid that, when the separation is too small, we add a insulator, means we insert a dielectric or insulator in between these two conductors. Okay, in order to reduce the force of attraction between these two. So now listen. So capacitor is a device that is used to store the electric charges or electrical energy, or it can also be called as a capacitor is a system of two conductors. It is a system of two conductors separated by an insulator. Separated by an insulator that is used to store the electric charges and electrical energy. This is called as a capacitor. And capacitance of a capacitor. Capacitance of a capacitor is defined as the ratio of charge on a capacitor. Ratio of charge on a capacitor to the potential difference between the two conductors of a capacitor. Right. So, it is the ratio of charge on a capacitor to the potential difference between the two conductors of a capacitor. That is called as a capacitance of a capacitor. And SI unit of this capacitance of a capacitor is, here the unit of charge is coulomb and unit of potential is volt. So coulomb per volt or farad. Coulomb per volt or farad is a SI unit of capacitance. Now let me move on to discuss about the SI unit of capacitance of a capacitor. We know capacitance of a capacitor is given by ratio of charge on a capacitor to the potential difference between the two plates of a capacitor, right, conductors of a capacitor. Suppose if the charge given to a capacitor is 1 coulomb and the potential difference developed between those two conductors of a capacitor is 1 volt, then the capacitance is given by 1 coulomb by 1 volt, that is 1 coulomb per volt, and coulomb per volt is nothing but a farad, right. So the capacitance of a capacitor is said to be 1 farad if the 1 coulomb charge is stored in a capacitor when the potential difference is 1 volt. Okay, so capacitance of a capacitor is said to be 1 farad when 1 coulomb charge is stored when the potential difference is 1 volt. This is called as a 1 farad. Okay. Suppose how to charge a capacitor. So this is for sake of remembering I am telling. So in order to solve problem, how to charge a capacitor. Okay, we are going to discuss that. So actually there are three types of capacitor. That is, one is parallel plate capacitor. One is parallel plate capacitor. And the second one is spherical capacitor. Second one is spherical capacitor. And the third one is cylindrical capacitor. Cylindrical capacitor. There are three types of capacitor: parallel plate capacitor, spherical capacitor, and cylindrical capacitor. Okay. Then capacitance of a capacitor, so depends on the size and shape of the plates of the capacitor. Okay, size and shape of the capacitor. It depends upon the size and shape of the capacitor. I mean geometry of the capacitor. And also it depends upon the separation between the two plates of a capacitor and the nature of the dielectric between the two conductors of a capacitor. Okay. Capacitance of a capacitor depends upon the nature of the dielectric that we are inserting in between the two conductors, and also the separation between the two conductors of a capacitor, and also the geometry of the capacitor. Geometry means size and shape like this. Okay. So there are three types of capacitor: parallel plate capacitor, spherical capacitor, and cylindrical capacitor. In your syllabus, we have to discuss about only parallel plate capacitor. So, and electrically, the capacitor is always represented by a circuit symbol by two parallel lines. Okay. So, this represents a capacitor. This is a symbol of capacitor. Okay. So, suppose if you write like this, now we call this as a variable capacitor. Variable capacitor means the capacitance of this capacitor can be varied, okay, to some value. But this represents the circuit symbol of fixed capacitance, capacitor of fixed capacitance. Say for example, it will be of 10 microfarad like this. It is fixed, we can't change this, so capacitance of this capacitor. But this can be changed from 0 to 10 microfarad. So this is a symbol of variable capacitance, capacitor of variable capacitance, and this is a symbol of capacitor of fixed capacitance. Okay. Now, how to charge a capacitor? In order to charge the capacitor, we have to connect the two conductors in a capacitor to a battery. Okay, we have to connect the two conductors of a capacitor to the battery. Now, before connecting it to the battery, it is neutral. I mean, both the conductors are in neutral phase. Suppose if you connect these two to the battery, now this longer line is positive terminal and this shorter line is a negative terminal. Okay, when you connect this capacitor to the battery, let us take this as a first conductor. So this is neutral, right? Since this is a conductor, there are free electrons inside this conductor, and these free electrons will move towards the positive terminal of the battery. So say for example, some 100 electrons are moving to this battery. Then it loses 100 electrons. Therefore, 100 positive charges are developed and this becomes positively charged. And now the electrons, if the 100 electrons are passed to this battery, then same 100 electrons will flow to this plate of the conductor, I mean this conductor of a capacitor. So this gains the 100 electrons, so it becomes negatively charged. For example, I am saying the number, okay, randomly. So now see, the capacitor is charged. Okay. Suppose if and the potential difference will be developed between these two conductors of a capacitor. Say for example, if I am giving 6 volt potential from this battery, then the potential difference between these two conductors will also be 6 volt. It cannot exceed this value because we are giving this much only. Okay. So up to 6 volt only the potential difference will be developed. So above this value the potential difference will not be developed between these two conductors. This is the maximum potential that capacitor can develop when you apply this much. Okay. Answer, that is expression for capacitance of a parallel plate capacitor. Okay. For that I have considered a parallel plate capacitor. That means a capacitor consisting of two conductors, and those two conductors are in the shape of the metallic plates. Okay. Now let us take, so the two conductors of this parallel plate capacitors are having the surface charge density. Conductor 1 is having surface charge density as plus sigma, and conductor 2 is having the surface charge density as minus sigma. And the charge of the first conductor is, first metallic plate is plus Q and the second metallic plate is minus Q. Let us take the distance of separation between these two plates of a capacitor is D. Okay. Now let us consider the first conductor. In the previous chapter itself, we already know in the case of an infinite thin sheet or in the case of a metallic plate, the electric field developed is E is equal to sigma by 2 epsilon naught. So this equation we have derived in the last chapter, right? That is electric field due to a metallic plate or a thin sheet, metallic sheet, right? So now here, the electric field produced due to the conductor 1, metallic plate 1 will be E1 is equal to sigma by 2 epsilon naught. Okay. And the electric field due to the second metallic plate is given by E2 is equal to, again the surface charge density is sigma by 2 epsilon naught. Okay. Now see, consider the three regions. That is, one is region above the conductor 1 and region below the conductor 2 and region between these two conductors. Now forget about this conductor 2. If we are having the conductor 1, since it is positively charged, the electric field due to this conductor will be, in the case of a positive charge, electric field lines are acting always outward, that means away from it, right? Therefore, here also the electric field is moving outward, away from this positively charged plate. Here also moving away from this positively charged plate, like this. Okay, let us take the electric field due to the first plate as E1. So here E1 is moving outward from the metallic plate 1. If we consider the second metallic plate, the electric field, since it is negatively charged, the electric field is moving towards this metallic plate. See, moving towards this metallic plate, right? This is electric field E2. Okay. Now consider the region above the first metallic plate. In the region above the first metallic plate, see, parallel plate capacitor means it is a capacitor that consisting of two identical metallic plates. Okay. So now see, here at a region above this metallic plate, electric field E1 is acting upward and electric field E2 is acting downward. That means the same magnitude of electric field but are acting in opposite direction. Therefore, the net electric field, in a region above the first metallic plate is equal to E1 plus E2. According to superposition principle, but E1 and E2 are equal in magnitude. So, we write E1 which is opposite to E2, right? Since E1 and E2 are having same magnitude, that is sigma by 2 epsilon naught minus E2 is also sigma by 2 epsilon naught. This and this gets cancelled. Therefore, the net electric field in a region above the first metallic plate is 0. Similarly, in a region below the second metallic plate also, see, E1 is in this direction, but E2 is in this direction, right? Therefore, since E1 and E2 are having same magnitude but opposite direction, similarly, in a region below the second metallic plate also, the net electric field is 0. Suppose if we consider in a region in between these two metallic plates, see, E1 is acting in this direction, right? And E2 is acting in this direction. E1 is also acting in the same direction. That means both E1 and E2 are in the same direction. Therefore, the net electric field E can be written as E1 since both are in the same direction plus E2. Now E1 value is sigma by 2 epsilon naught plus E2 value is sigma by 2 epsilon naught. Here, the denominator is same. We can take the LCM as 2 epsilon naught. Now sigma plus sigma is 2 sigma. This 2 and 2 gets cancelled. Therefore, electric field between the two plates of a capacitor is always equal to sigma by epsilon naught. Please keep it in mind. The electric field between the two plates of a capacitor is always equal to sigma by epsilon naught. Electric field between the two plates of a capacitor is equal to sigma by epsilon naught. Okay. Now, we need to derive expression for capacitance of a parallel plate capacitor. For that, let us consider. We have derived expression for electric field between the two plates of a capacitor as E is equal to sigma by epsilon naught, right? Sigma by epsilon naught. The sigma is the surface charge density. So surface, according to the definition of surface charge density, we write it as a ratio of amount of charge per unit area of the surface. That is, charge to area is called as a surface charge density. Ratio of charge to area, that is Q by A. Now substitute this to this equation. Therefore, we can write E is equal to Q by, so A into epsilon naught. In place of sigma, I have written Q by E. Okay. Now, we know the relation between the electric field and the potential difference, that is E is equal to minus dV by dl, general relation. Okay. If we consider only magnitude, this negative sign will be avoided. Okay. Here the potential difference between the two plates of a capacitor is considered as V, and the distance of separation between those two conductors is D. So, E is equal to, we can write V by D. E is equal to V by D. Right. Now substitute this. So, here we can write V by D is equal to Q by A into epsilon naught. Now take this Q to this side. Okay. Or V to this side. Just cross multiply. Okay. So we can write, if we cross multiply this, V goes here, A into epsilon naught goes here. So we can write, so this term as A into epsilon naught by D is equal to Q by V. We already know the amount of charge given to a capacitor to the, so potential difference between the plates of a capacitor is called as a capacitance. So, Q by V can be called as a capacitance of a capacitor. Therefore, we can write here as, so C is equal to, in place of Q by V, C is equal to A epsilon naught divided by D. Okay, this is the expression for capacitance of a parallel plate capacitor when the space between the two plates of the capacitor is air or vacuum.